I want to play another interview first, which is I happened to catch up. I got an email from Owen Madge, who is from the Steel River Rocketeers up north England, sort of Newcastle-y kind of way. He was talking about one of my favourite sort of concepts, which is to launch from a balloon, which is called a raccoon.
Beautiful.
A rocket from a balloon. Or raccoon. And he's in a race. He's in a race with Sir Richard Branson, of course, because Sir Richard Branson might be the first person to fly something out of the UK that goes into space above the Kármán line.
Yep.
So might our friends over at Orbex as well.
Yep.
So might Skyroarer. But so might this bunch of, researchers and students and rocket enthusiasts who've got this little club, and they're trying to build a something that will go over the Kármán line, and it launches from a balloon. And so I thought this is like the absolute opposite end of the spectrum of SLS. So I thought I'd put in a quick little interview, and I really like it. He's a really good guy, and he reached out. So
I'll even before I hear the interview, I think I'm going to be rooting for the raccoon.
Yeah. Well,
got to support the underdog.
You always, as an Englishman, you have to support the underdog at all times. Yes, and Dickie Pickles, and this particular instance isn't the underdog. Yeah. He's the overdog. Right. So here is
go raccoon.
Yeah. So here is my interview with Owen.
The Interplanetary Podcast, putting the ace back into space.
So I am joined on the podcast by Owen from Steel River Rocketeers. Welcome to the podcast, Owen.
Thank you very much, Matt. It's great to be on.
Good. Whereabouts in the world are you?
I'm currently in Spennymoor, so northeast England.
A bit of an undiscovered part of the world for most of our listeners, I'd imagine. But
full of natural beauty.
Full of natural beauty. It really is. It's a beautiful part of the world. You asked to come on the podcast, and I think it is a really, really interesting project that you've got going. But before we get onto the sort of project that's coming up, tell us a little bit about the Steel River Rocketeers.
Oh, yeah, of course. So Steel River Rocketeers, it's basically a student-led launch vehicle development program, and our main goals at the moment are to educate people in the region, inspire any sort of work into space, and showcase the diverse skill sets that the region has to offer. We're mainly working within Teesside and the surrounding area in the northeast, but we've started working all the way across the UK now, and we've had a variety of members in the past, not all of which have been students, but all of them have had an extreme interest in engineering and a very keen willingness to learn, which is the main thing that we require on the program.
Indeed. So, yeah, well, tell us a little bit about your latest project and some of the sort of milestones that you've already reached and the ones that you hope to do later.
Yeah, of course. So the latest project that we're working on, overall, we're working towards our developmental launch vehicle, which is SR1 or Steel River 1. SR1 is a little raccoon, so a rocket and balloon combination, and it's composed of a 1,000-gram natural latex rubber balloon, meteorological balloon, and an inbuilt stabilized launch pad, or we like to call it the cup, and then that carries a small rocket no larger than an A4 sheet of paper, which is powered by an APCP fuel grain. The rocket launches at 30 kilometers from inside of the balloon above the ocean, and only if all of the launch conditions are met. So we have a lot of different electronics on the launch pad, on the rocket, for example, to check up a lot of pre-flight conditions. So one thing about the rocket is that we use gyroscopic stabilization, because obviously launching at such a high altitude, you'd need to accelerate to a very high speed to have any sort of stabilization from just fins. So we like to use gyroscopic stabilization just to get that initial stabilized bit of flight there. So one of the conditions, for example, is to make sure that the rocket isn't wobbling on its spin-up mechanism while it's rotating at about 20 rotations per second. So as long as that one condition, and then obviously a few other conditions, one of which being that it's pointing vertically upwards. Once those conditions are met, the rocket then launches from the 30 kilometers, bursts through the skin of the balloon with its needle skin tip, accelerates to Mach 5 within a 7-second motor burn, and then this will hopefully achieve apogee above the 100-kilometer Kármán line.
So it is. Yeah, so it's a suborbital launch, isn't it?
It is, yeah, ballistic trajectory suborbital launch.
Yeah, so I mean, just as a little bit of background for some of the listeners who aren't super clued up, and I do love the name Raccoon, and this has definitely been one of my. I've always been really interested in this idea of launching rockets from balloons, and I suppose you're in a kind of race with another rocket launch system. That avoids the rocket equation for a large proportion of the flight. So it avoids the trying to get off the ground. Because, I mean, just to put it as bluntly as possible, a rocket carries all the fuel that it uses, and which makes it kind of a bit annoying because most of the fuel it uses is to carry the fuel that it needs to use later on.
Exactly.
Exactly. So you've got round this by using a balloon to carry up to a certain altitude, but you're in a race with old Dickie Pickles at Virgin Orbit, who uses a jumbo jet to carry his rocket to a certain altitude.
Exactly.
But the scale is somewhat different, isn't there? Is there a sort of scale? Is there a scale constraint on the Raccoon style rocket? Do you know?
Well, effectively, your main constraint is the balloon that you can use. So I've seen recently NASA's experimentation with a lot of super pressure balloons taking up quite high weighted payloads, and obviously the more pressure your balloon can support and the bigger it can get, the higher payload you can take. So ideally, if you're talking for an orbital payload, something like that, where you need a significant second stage to be able to drop it off into orbit, you'd be talking probably much larger balloon than what we're using now. If not, I suppose you could probably use more than one balloon if you're willing to suspend the package from below. But our system currently, it sits actually inside of the balloon. So the cup is effectively a sort of stopper on the bottom of the balloon neck, and then launches from inside, which offers a few more advantages to a normal ground launch. As you say, Dickie Pickles is off with his jumbo jet, but with it being inside of a balloon, we can launch in the vast majority of weather conditions, because obviously, since we're coasting up to 30 kilometers of altitude before we actually launch, up in the stratosphere, the vast majority of weather conditions are completely mitigated. So it's quite a robust system that can launch at quite a lot of different times, and I'm hoping that if something causes Dickie Pickles to get a little scrub in there, we might be able to run in under his nose and grab the title away from him.
Well, yeah, and that title up for grabs is the first people to go above the Kármán line launching from the United Kingdom, right?
Yep, that's exactly right, from the UK mainland. We're also aiming for the first student group to be able to independently verify that we've passed the Kármán line. I believe
would that be globally? And that would be globally.
Yeah, I believe so. There was a student team in the US that managed to pass the Kármán line, but that was not independently verified. So I think that they did manage to pass it, but obviously no one's sure. So if we could do it, then we would be the first verified space flight from an all student team.
Yeah, well, that would be an achievement in itself, wouldn't it? So what's the gas inside the balloon?
Helium at the minute. We're using helium mainly because it's inert and it just simplifies a lot of the launching a rocket engine from inside of a gaseous atmosphere. It simplifies a lot of the issues, but obviously with it being a scarce resource, we are looking at converting over to hydrogen in future. But as I say, it's got a lot of disadvantages compared to helium when it comes to its inertness, if you will. But yeah, as I say, less scarce, so a lot cheaper, a lot easier.
I guess if you've got electronic systems or things spinning up, any spark or friction sets the whole thing on fire. If it's hydrogen, exactly. Is that the thinking basically?
It is, yeah. I mean, it's possible to if the rocket were to ignite in a hydrogen atmosphere, it's possible that the brief amount of time that it would be in there would be acceptable to not alter the rocket's trajectory. But it's playing with fire in a literal sense, so yeah, we're not 100% sure yet. But more testing in the future, and we'll see if we can get to something hydrogen based instead of helium.
And what sort of milestones have you done so far with this particular launch system?
Well, we've achieved a fair bit so far. One of the things that we focus on is educational outreach. So we've been working quite a lot with the students at Eaglescliff School on our model rocket flights. These are basically just different staged flights trying to get different altitude milestones up to 1 mile from the ground, because that is a rough equivalent of the engine grain that we'll be launching at 30 kilometers. Interestingly enough, if we launched our 30-kilometer engine from the ground, it would only reach about 1.6 kilometers of altitude, whereas launching it from 30 kilometers, it actually enables it to reach an extra 72 kilometers of altitude. So hopefully 102.
Yeah. Is that presumably that's all just down to atmospheric drag?
Yeah, that's exactly it. I mean, stratosphere, you're above 99% of the atmosphere, and with the lesson of drag, the lesson of necessary propellant. So it allows us to have a very, very light launch vehicle, and also the possibility for scalability in the future.
Yeah, and presumably the actual rocket itself doesn't need to be so robust because it's not reaching such high temperatures and max Q and all those elements.
Yeah, exactly. That's another thing. I mean, the aeroframe that we're currently using is a 3D printed. I believe it's either PLA or ABS. I'm not 100% sure on that. But just a 3D printed plastic aeroframe, which obviously wouldn't be great from a ground launch perspective when you hit max Q and pressures such as that.
And of course, the fairing has dual use because the fairing itself, you're saying, actually pins the balloon and bursts the balloon on its way through.
It does, yeah. It will have a pin extruded from the top of the fairing, so that'll contact the skin and then pop the balloon as it launches. And we've done a lot of testing on the ground for this as well as like other various tests. I think we're up to about 20 different balloon flights now. We've done, the first test that I was involved with was the MicroMars payload test, where we launched a payload suspended from a balloon. Mm-hmm. That worked very well. We recovered it out of a tree from a parachute. To be honest, it took embarrassingly long for a group of engineers to figure out how to make a longer stick out of two long sticks. But we got there in the end. A couple of shoelaces were involved, but we got there. And as you say, the penetration tests we've done on the ground as well, and all sorts of different power ratios we've done for motors, and we've not seen any sort of significant deflection from that either. So just because it's the balloon skin so taut when the pin impacts it, it just retreats straight away from the pin and doesn't create much friction. Yeah,
and I guess someone might be asking, why not just ride the balloon all the way into space?
Well, yeah. I mean, that would be an ideal world, but obviously, once you get above a certain atmospheric pressure, the balloon expands to a rate at which it can't contain the pressure within it. Let alone that balloons work on a buoyancy principle. So once you've escaped the atmosphere, you've no longer got a fluid to become buoyant in. So there's a limit to the height that you can reach with a balloon.
Yeah, it's just always so pesky, isn't it, to get off the Earth? Everything seems to go against you. So, what's the desired? What sort of payloads are we talking about here for this rocket?
Currently, for the Steel River 1 rocket, we'll be taking up a bit of a simplified payload. So it'll be mainly made up of a GPS module, a few transceivers for communication, and a HD camera for capturing the flight itself, which obviously with using gyroscopic stabilization will be a little bit spinny to start with. But hopefully once it's no longer in powered flight and it's climbing to apogee over the course of 2 minutes, the air resistance, or at least what's left of the air resistance, will hopefully slow the spin down. But the payload that we're hoping to take up on later flights, suborbital flights, would be the ThumbSat module that our mentor and chiefs created. It's a small CubeSat platform that's below 14 grams in weight, and then you can take upwards of about a 25 gram payload on top of that. So the end flights, once we've actually achieved space and we're starting to drop off packages for experimental use, those will be of around that order of payload. But the rocket that we're using for SR1, I believe the dry weight payload is 160 gram dry mass and 200 gram fuel weights for a total of 360 grams.
And that's the whole system.
That's the whole rocket. So weighs less than a Coke can, actually.
Yeah, so it's so give us some sort of idea of size. Is it like a sort of Coke can in size?
Yeah, I mean, roughly, we're talking less than the size of an A4 piece of paper, so around the length of a 2B pencil. It's quite a small, very small rocket, but it's quite advanced for a solid rocket. It's got a complete aluminium motor house and motor case, and it's got a vacuum expanded nozzle, so it's designed for vacuum flight. So obviously no thrust whatsoever on the ground, but perfect up at 30 kilometers altitude. But yeah, it's quite an interesting little rocket, to be honest, for basically being a model.
Yeah, absolutely. So tell us a little bit about your mentor then. Is this Sean Whitehead? Is that the guy?
It is. So I'll just give you a little bit of background first. So Steel River Rocketeers is kind of three groups working together. You've got ThumbSat over in Mexico. You've got Scoutech, in the UK, and then of course SRR in the sort of Teesside area in the UK. ThumbSat is the group responsible for the design and production of our femto satellites, ground stations, and most of the software that we use. It's mainly designed and built by Dr. Antonio Hernandez, who works in our clean room production facilities in Mexico. Scoutech is Sean Whitehead's personal R&D company. All of this has been started by Sean, but his primary involvement, I would say, is in his R&D company. And that's the group responsible for the manufacture of most of our hardware, such as the motor casing and nozzle. And then, of course, there's SRR, which is the student team responsible for taking all of these parts, putting them together, and flying research missions, ultimately with the goal of reaching space. But he's done a lot of work in the past, ranging from working on the Beagle 2 Mars lander, or some instruments that were on the Beagle 2 Mars lander for the British Interplanetary Society. And he's also worked on projects including robotics, exploring the chambers in the Great Pyramids. He's also been working on a project to place a sculpture on the lunar surface. And the latter of these projects was kind of presented him with an issue, which was how do I cheaply and reliably test a small sample of material that I want to use for the sculpture in a high energy particle vacuum environment. Obviously, in order to do this, a CubeSat would be the best sort of choice. But with the current launch programs and the launchability of CubeSats, you've got to look at a rideshare. Rideshare is very expensive and a large wait time as well. So it just became very obvious to him that there was a massive market out there and a need for this sort of low cost, low fuss and short wait launch system. So that's basically what we're doing here, is trying to create a launch system where we do the paperwork, we launch the rocket. All the customer has to do is provide an experiment that fits within the mass budget and works with the ThumbSat satellite bus.
So I would assume then. So the overall goal is to get things into orbit, which obviously requires a little bit more delta V, a little bit more thrust to get things into orbit. You'd need to, presumably for testing materials against radiation, you'd have to maintain some form of orbit for it to have any kind of a reasonable time exposed to that radiation.
Definitely. So the flights that we're using at the minute are about 8 minutes of microgravity time, but then obviously there'll only be about 30 seconds to a minute of that above the Kármán line. So exposed to that sort of high energy environment, it's not going to happen on a suborbital flight really. So we are aiming for orbit in future, but as you say, it's quite a significant jump. So it'll take a little while past getting the space shot out of the way. But no, I mean, as I say, the system's very scalable. If we add another balloon, for example, you've got double the payload weight. Realistically, we're well below the payload limit of the balloon that we're even using at the moment. So realistically, it's very possible that we could get orbit quite soon after the fact. I mean, I say soon and long at the same sentence, but I'm hoping for the latter. I'm hoping for it to be as quick as possible.
Yeah, well, obviously, in what I've noticed in the world of rockets is everything happens much quicker than everyone thought.
Yeah, exactly.
Not so. Yeah, so it's always. I mean, let's face it. It's incredibly difficult to get things up to the Kármán line. I don't think anyone other than rocket scientists really appreciate just how difficult it is. It's a common question that I always get is, why don't we go to the moon all the time? It's like, well, because it's insanely difficult. And so I absolutely wish you all the luck in the world. I kind of am rooting for you in a way to beat Dicky Pickles or Orbex or Skyrora to be the first people to launch from an orbital launch from the UK. It'd be absolutely brilliant. But what an exciting time, that we might see over the next couple of years. Quite a few different methods of getting above the Kármán line by lots of different from the UK. I mean, who would have thought?
I've got the horizontal launch facilities being built up, got the vertical launch facilities. It's going to be quite an exciting time to be walking about the island like.
Yeah, it's quite a good time to be an interplanetary podcaster.
It is, it is.
I'm winding myself up for it. Well, thanks very much. Thanks very much for coming on the program. But where can people go and check this out? And have you got a call to action?
Of course. So we really are trying hard to accelerate the launch date to get this space shot out of the way. But obviously, the best way to do that is more hands on deck. And we've had a little bit of trouble with colleagues throughout the pandemic and stuff. So we are looking to get as many applicants in as we can. As got plenty of room for recruitment. So if anybody's interested, you can find out more information at www.steelriver.space. If you scroll down to the bottom of the page there's an application form and you can fill that out. Or you can just email me directly. That's owensteelriverspace@gmail.com. And just to specify, it's OWAIN steelriverspace@gmail.com.
Well, thanks very much for joining me on the podcast, and I wish you all the luck, and I'm sure the Spodcats will too.
Thank you very much. No, it's been a pleasure being on, Matt. Nice to speak to you.
You're listening to the Interplanetary Podcast, putting the ace back into space.
There you go. That's the weird concept of launching a very, very small rocket, and it's only you have to see the pictures, Rob, because it's just a little bit bigger than a Coke can.
Sounds amazing.
It is.
I'm going to have to take a proper look at it.
God, if they manage to do it, it will be absolutely awesome. That whole idea that there'd be the first sort of volunteer group or sort of amateur group to get over the Kármán line as well would be pretty phenomenal. So there must be a bit of a rush on around the world for that as well, I would have thought.
Yeah, and only being the size of a Coke can, they'll probably be spared idiots like me complaining about the quality of the interior.
Well,
anyway, tell me about your decor.
Yeah, I did see inside. It was a little bit. If you were an ant, you'd be pretty disappointed with your accommodation.